Hello, I am Manuel Lopez. I'm Assistant Professor in Sustainable Wireless Systems at CG Flagship Center of Wireless Communications at the University of Oulu, Finland. Today I'm going to be talking about sustainable Internet of Things and specifically on radio frequency wireless power transfer technology. The main topics I will be covering are related to sustainable wireless systems in general and how wireless power transfer technologies come into play here, and specifically radio frequency wireless power transfer. I will be talking about prospects, challenges, enablers, solutions, and research directions. By the end of the talk, I will also be answering or try to answer a question related to whether 6G will provide RF wireless power transfer as a service or not. And I will be discussing the conclusions by the end. So, sustainable wireless systems. Usually when we talk about sustainability, we think about something that is green and that is environment friendly. But sustainability is a much wider concept. It's an assemblage of mutual interests between social equity, viable economics, and a healthy environment. And the sustainability model can be represented as this triangle here that personifies a synergistic integration of these three main competing interests, including equity, environment, and economy, what is known as the 3 E's. In terms of equity, the aim is at attaining social justice and fair economic opportunity. In terms of economy, the aim is at attaining sustained economic growth and efficiency. And obviously, in terms of environment, the aim is at green solutions protecting the environment. So sustainable development is basically a green, profitable, and fair development. Back in 2015, the United Nations formulated 17 Sustainable Development Goals for the Agenda 2030, which are related to these three aspects to a greater or lesser extent. Here it is important to keep in mind that the advancement of one of these development goals can be detrimental to others. For instance, consider massive network densification, which is beneficial for industry and economic growth in this sector here. But at the same time, when you increase the network equipment everywhere, which is basically network densification, you are also producing more e-waste, and processing this e-waste becomes a very challenging issue in terms of environment friendly solutions. So it is fundamental to keep the three aspects of sustainability in mind. It's not only about economic growth, it's not only about the environment, it's not only about equity, but it's an assemblage of mutual interests between these three factors. Let's continue. Wireless systems and networks are evolving to support connectivity, processing, actuating, sensing, data, and intelligence everywhere. That's the vision of the Internet of Everything and also of the 6G wireless systems. And to support such massive number of devices and heterogeneous systems, it is fundamental to reduce the dirty energy consumption to the minimum, mitigate the e-waste, enable long network lifetime, with low cost of maintenance while still providing and supporting stringent quality of service requirements. And given the complexity and massiveness of these kind of networks, the main two problems here are related to the charging problem and the energy consumption problem. So we will go to discuss them in the sequence, but the main focus will be on the charging problem, as we will see. Basically, every technology that enhances the system performance according to some metric, for instance the throughput, has the potential to do the same and minimize the energy consumption if such other performance requirements is fixed. So even though there is a set of technologies for which this is even more evident, and these are the ones that we illustrate here. So AI, for instance, is becoming a fundamental component of wireless networks. So it is important to keep them energy efficient, both at the network side and the device side. The network side, it is important to enable energy efficiency via mobile edge computing and digital twins mainly. And at the device side, we need to have very simple AI algorithms to run on these energy constrained devices. And that is the concept known as tiny AI. We have also new devices emerging, as is the case of these reflect arrays or metasurfaces. These are passive or semi-passive devices, so they consume little energy, and still you can shape the environment and the channels as required. Also, there is a more let's say older technology which is backscatter communication, but still the communication standards for these are not quite broad, so we expect much more advances in terms of backscattering and much more use cases in the next years. Also, there is the possibility to integrate with non-RF technologies and use energy that is already in the environment as the light. We can modulate incoming light or use VLC directly to promote energy efficiency as well. And of course, there is coverage extending technologies which allow promoting energy efficiency in the same way as you can promote throughput, you can promote, of course, energy savings. And these are the case mainly of cell-free MIMO and massive MIMO and satellite communications, and also connectivity from the skies with UAVs and moving APs. As for the charging problem, observe that at one hand, the number of IoT devices is nothing but growing in the next years. You can see here this curve, the violet curves represent the number of IoT devices deployed in 2020, 21, currently in 2022, and the ones that are expected by 2026. And it is interesting to see that compared to traditional ICT equipment like PCs, laptop, tablets, and mobile phones, their number is increasing. So there is a high increase in number of IoT devices, and for them, it is difficult to power them using traditional technologies, like, for instance, the wire solutions. If you use wires to power such number of devices, you are creating a mess web of wires, which often are difficult to deploy everywhere and require high installation costs, deployment costs, etc. In case of IoT devices equipped with batteries, well, you are promoting the e-waste generation problem. Also, there is an important constraint, and it is that using batteries constrain significantly the form factor of the devices, in terms of that the batteries are the main factor affecting the size of these devices. And of course, you have the high OPEX feature because you need to run maintenance tasks over them to replace or charge these batteries. So it is questionable whether these solutions will be scalable, sustainable over time. On the other side, and of course, these two issues scale with the number of devices. The more we have, the more critical these problems are. On the other hand, the increase in the number of mobile phones, PCs, and laptops, etc., the traditional ICT equipment, is expected to grow very slowly in the next few years. So it's not critical than the increase in number in this case. But people want to stay connected. With wire charging, you cannot really move, while wireless charging solutions available today are of short range, and one still needs to connect the device for charging from now and then. So there is a craving for more flexibility in the charging process in this equipment. And there are two main technologies that are suitable for addressing these issues. And one is energy harvesting from renewable sources, and the other is wireless energy transfer. The first one is basically related on how to obtain the energy, from which sources to obtain the energy. And the second one is related to how to deliver this energy to the devices in an efficient and sustainable way. There are several technologies for wireless power transfer. They can be classified according to the energy source that is utilized. For instance, it can be piezoelectric, electrostatic, acoustic, induction, magnetic, and also RF. And this is the energy source. The levels of energy that they can provide is also can be very different in different orders of magnitude, and also they can have different hardware complexity, different limitations, characteristics. So we can say that there is no one-fits-all solution when wireless power transfer. When we're talking about wireless power transfer, as in many fields of engineering, there is no one-fits-all solution. So the right solution depends on the use case. For instance, inductive coupling has been used already in several devices that are nowadays available, like the electric toothbrush to avoid electrocute due to the liquids. There is also wireless power medical implants and also the QI standard as well. As for the magnetic resonance coupling, we have, for instance, the Qualcomm E-Zone for wireless charging, this Qualcomm prototype for halo electric vehicle charging, and even this higher wireless power HTTP. In terms of electromagnetic field radiation, for instance, we have this laser power beam charge UAV. We have also this PowerCast RF harvesting circuit for sensor networks, and even this Intel tag, which operates with RFID. The main scope of this talk is on radio frequency wireless power transfer. Well, why is that? To begin with, let's see how this works. Basically, we have an energy transmitter, which is any node that transmits RF signals. We have the medium, and we have an energy harvesting receiver, which is basically composed of a bandpass filter, well, the antenna, the bandpass filter, a rectifying circuit, and a low-pass filter. After this, we have the DC harvested energy or current. Of course, this RF transmitter can be dedicated or not. I mean, we can harvest energy from cellular signals, or we can have dedicated deploy nodes for the purpose of transmitting energy. Of course, if we rely on non-dedicated energy transmitters, then the amount of energy that we can harvest is very little and depends on the geographical position of the nodes and the traffic activity in the given hour, etc. While if we have a network of devices deployed to this specific purpose, we can somehow control the energy availability in the devices. And that's the main purpose of radio frequency wireless power transfer technology. And of course, as I was commenting before, this technology might not be suitable in all the cases. We have a comparison here, qualitative comparison in terms of range, for instance. The main benefit in comparison with magnetic induction and electrostatic wireless power transfer is that its energy efficiency doesn't go to zero immediately, so it is possible to transfer energy in the order of meters. While the efficiency in the near field is very little compared to these other technologies. This is a far field radio frequency wireless power transfer technology. And also the good side is also that it allows very little form factors, so you can equip this technology in very compact size devices. It allows intrinsically multi-user operation, mobility, but the harvestable energy is very little, and you need to try to enhance the energy transfer efficiency here to make the technology sustainable at the end. And as I was commenting, in this figure here we have like an information node that is transferring energy to the devices, and we have a dedicated energy transmitter as well. Different to information transmission networks, where we can transmit information over long range, the harvestability zone around energy transmitted is very limited because of the channel path loss. So usually you can harvest energy when you are close to energy transmitter in the order of several meters. And if the transmitter is a very powerful device, like transmitting in the order of kilowatts or megawatts, then it is possible still to harvest in the order of few kilometers of distance, but very little energy. And you can have this infrastructure-based system or this infrastructure-less system where the devices interact among each other in a hot way. But how radio frequency wireless power transfer may be an enabler of sustainable wireless systems? Let's discuss a bit about this. So, in terms of environment, this technology can promote the reduction of e-waste because we can avoid the use of charging cables and traditional batteries and the reduction of form factors. It is possible to reduce the maintenance operations and, of course, the corresponding carbon footprint. And there is also potential for self-sustainability if we leverage energy harvesting as well. So if you use energy harvesting from renewable sources to power these radio frequency energy transmitters, then the whole system becomes green and therefore is more prone to support sustainability. In terms of economy, these networks are intrinsically of low capex, so low deployment and installation costs, this means, and also there is potential for low OPEX, and it can support many futuristic use cases with high economic revenue. And this is already captured by the predictions. For instance, in the near technology, we are forecasting a 6-fold increase in the next 8 years. So from 2020 to 2030, in the next decade. And in terms of far field technology, you know that the market is still very low, but there is expected a 7-fold increase by 2030. And also see, these are the number of devices which operate with battery in 2020, and the ones that operate without battery in 2030. In terms of equity, there is also the possibility for enhanced and reconfigurable accessibility to the charging services. Since we can deploy these RF energy transmitters more easily, we can provide charging service in a more location independent way, so we can promote more accessibility to the charging services. So there are several challenges in realizing completely sustainable wireless power transfer technologies, specifically radio frequency based. And this is because, first of all, the low end-to-end power transfer efficiency. So there are 3 main components in these kind of systems: the energy transmitter, the channel, and the energy receiver. And each of these components has its own efficiency term. The whole efficiency of the system is the product of them, if they are independent, of course. And specifically, the wireless channel is the one that introduces the bigger losses, because the path loss is directly proportional to the wavelength, to the square of the wavelength, and inversely proportional to the square of the distance. So if we operate at 1 gigahertz, and we transmit a signal of 1 watt to a distance of 1 meter, we can only harvest at maximum 5.7, or let's say 570 microwatts. If the distance goes to 10 meters, then this becomes 5.7 microwatts. And of course, in real, these channels are more lossy, and the expected path loss is much greater than this in reality. So we need to compensate for these losses at the transmitter and at the receiver. Also, there is a fear of wireless because with the advent of the 5G systems and the exploitation of the high frequency bands, people are fearing more and more about the potential impact to the human health of this high frequency transmission, even though they are non-ionizing, so they cannot change the structures of atoms and molecules, so they cannot produce carcinogenic effects in reality. But still, some biological effects are possible, like a little raise of temperature in the skin cells or so. So that's why international bodies have set electromagnetic field constraints uh, on the radiation of these signals, which are very important. But still, we need to find mechanisms to fear and to erase the fear of wireless in people. And also there is the lack of technology standardization. But this is mainly related of the first and the second aspect. So if we can promote systems that are more efficient and are more transparently complying with electromagnetic radiation constraints, then we can promote more standardization attempts and make the solution to scale quickly. So let's discuss now about some enabler solutions and potential research directions, and we will be exemplifying with few of our recent works on the field. So in terms of low end-to-end power transfer efficiency, the strategies that we can implement to improve the efficiency of the energy transmitter are basically relying on optimizing the power amplifier efficiency, using multi-antenna waveform intelligent scheduling. So to compensate the wireless channel, we need to use intelligent scheduling and also promote coverage extended technologies. And for the energy receiver, we need energy efficient architectures, also multi-antenna technologies, and appropriate waveforms such that the energy harvesting circuit can harvest the most energy, of course, out of it. So as you can see, some of the strategies impact different blocks. So this means that we cannot rely on independent optimization of these blocks by their own. So we need to have an end-to-end optimization of energy efficiency. And this is very complicated because each of these blocks is very difficult to model. So this promotes the use of learning or data-driven approaches to solve these kind of problems. And of course, we can also optimize the power load. I forgot to mention this, using intelligent scheduling of the devices. So the fear of wireless, well, there are two main metrics to regulate the electromagnetic field radiation exposure or to characterize it. And this is the maximum permissible exposure, MPE, and the specific absorption rate, the SIR. And these regulations minimize the potential biological effects like tissue heating, or which is caused by radiofrequency radiation. Specifically, the MPE constrains the level of incident radiation specified in watts per square meter, while the SIR measures the absorbed power in a unit of mass of human tissue by using units of watts per kilogram. And this specifically is a relevant metric when operating close to the transmitter. For instance, all the mobile terminals are subject to this kind of constraints, just to say something about it. And of course, to make the technology sustainable at the end, we need like a holistic optimization taking into account all the factors that affect the performance. For instance, the energy transmitters or power beacons affect the medium, and through the medium they power the devices, but the medium can be influenced by the use of reconfigurable metasurfaces and sensing nodes to detect the presence of living tissues or other obstacles. And This can be managed locally and globally by different processes and different kind of AI mechanisms. So a holistic optimization for this process is needed. Let's discuss now a few of our recent works. For instance, one of the main directions that we have been working on in the last year is related to massive radio frequency wireless power transfer. Here the problems is related on how to power efficiently a massive number of devices that are in the neighborhood of a certain energy transmitter. The thing with these devices is that they are very low power devices, so the use of traditional CSI beamforming, multi-antenna beamforming at the energy transmitter to power the devices might not be feasible in these networks because we cannot use that amount of energy to train the channel and know the channel state information here. So that is why we've been proposing some CSI-free or limited solutions such that this energy transmitter can power a large number of devices simultaneously without or with limited information of the channel. And what are the advantages of using this mechanism? Basically, we will be relying on the statistics and structure or the loss component of the channel. And the advantage is that these statistics remain accurate over a large time scale, especially in static and quasi-static setups. They might be predicted using machine learning or statistical methods. Usually in case of loss channels, they are geometric. So basically you can determine or predict easily based on the geometry of the antennas and the position of the device. Well, you can rely on these statistic or deterministic components of the channel when you cannot spend much energy, while you can rely on instantaneous channel state information when you have favorable energy conditions in your system. That's the basic idea that we proposed. And some of our works on this matter are these, and you can consult them for more details, but we will be discussing some of them in the next few slides. Let's say, for instance, that we have a linear antenna array at the power beacon or energy transmitter. So this is a linear array of M elements. So what can we do if we don't know the channel? Basically, we can implement a switching antenna strategy such that we transmit with one antenna only at the time. And in that case, we can exploit the channel or the spatial diversity of the system. And you require only one RF change because you will be transmitting with one antenna at the time only. In that case, you create this omnidirectional radiation pattern. But although you can exploit the diversity, you cannot exploit any average gains of the system because you are not creating any beam, in fact. What else you can do? Well, you can implement some kind of analog beamforming by phase shifting the signal at each of the antenna elements. In this case, this radiation pattern is attained if we don't implement any phase shift. Basically, the signal is being formed towards the body side of the antenna and the other complementary direction. And you create beams in these directions and some lateral beams in this other. So the devices that are in these directions can perform very well. But then there are these other devices that are not favored at all, and then they can harvest very little energy. We realized that a beamforming if you phase shift the antenna, the signals and the consecutive antenna using these shifts like 0 pi, 0 pi, 0 pi, then you can create this radiation pattern, which is more favorable than this one because these beams are wider. But still, there are certain positions where you cannot harvest much energy because they are in the nulls of the beams. So this is a difficulty that we solve it in the next strategy. What we did was to make it rotate the previous beamforming. And when we do this continuous rotation using like a stepper motor or other similar rotary mechanism, then we can create this semi-omnidirectional radiation pattern because you are averaging over time. And the interesting thing with this is that you don't only attain diversity gains, but also average harvesting gains. and the average harvesting gains scale with the square root of the number of antennas m, which is very good because no other strategy without any channel state information can attain this. Also, there is a side effect, side advantage is that it is more likely to reach those devices that are blocked if you implement this rotary mechanism, because it is more likely that at some rotation you can reach the device through some non-line of sight channel, and then you can harvest these powers even though there is no line of sight. So that's what we did, and we also incorporated some SAR constraint to this system such that if we detect the presence of a human, we can control the power such that we reduce the power of the beams where the human or the human tissue is detected, and we made the beams in the other directions stronger. In that case, we can operate with the same amount of total energy and still obey the SAR constraints. For more details on how this can be modeled, you can refer to this paper. Interesting thing here is that when you implement this rotary mechanism, you can even outperform the operation of the full CSI system. So this is very interesting because you don't require any signaling overhead and the corresponding energy expenditure, and you can still outperform the system as if you had a full and perfect channel state information. You can observe this. The proposed rotary mechanism is the orange one, and you can see that as you increase the number of devices that are being powered above 16, the operation with the rotary mechanism is much better than the one with full CSI and the other CSI-free strategies. And in this case, we're showing the performance as a function of the SAR constraint. But this is a bit more complicated to explain, so I will let you have more details about this in the specific paper. So other research direction in the massive radio frequency wireless power transfer front is related to the multi-power beacon deployment optimization. So here the idea is how to deploy these energy transmitters, also called power beacons, so that you can ensure that the service area or the charging area is performing as expected. I mean, that you are in fact powering the devices with the minimum required energy by design. And this problem has been investigated by our group in some recent papers where we define how many power beacons are needed to power a certain area and what can we expect in terms of performance if they are operating with CSI-free multi-antenna beamforming. But let's discuss a few interesting research directions in these topics. First of all, we have only investigated CSI-free schemes when we exploit a linear arrays. But what happens on the other technologies, antenna technologies like circular, rectangular, etc. Technologies, multi-antenna technologies. So what is the optimal antenna array topology? That's an interesting question. Also, it would be good to investigate the optimum placement orientation of the antennas in a multi-power beacon scenario. You know that some of the CSI-free strategy that we discussed, they create some beams, so you don't need to take care only about the position of the energy transmitted, but also the orientation of the antenna. Also, it is important to investigate what gains can be achieved if we have a multi-power beacon scenario and we implement these rotary antenna strategies. So what gains can we achieve with this? And also we haven't considered the energy that is consumed in the rotary process. And what is the scale of the gains if you consider this energy consumption? Of course, it must be understood that this energy consumption is at the energy transmitter side, not at the device side. So that is one inherent advantage compared to the others. But still, it's important to see how much efficient the system can be if we consider these energy sources, consumption sources into account. Another scenario of practical relevance is how to power or how to realize high power wireless charging. And the main scenario of interest are illustrated here. So the idea here is to charge more energy demanding devices, such as wearables in a room uh, or robots in a factory scenario. And the key question is how to make the charging system sustainable over time and competitive with respect to state-of-the-art charging solutions. And special attention should be put to the safety component, since in this case the radio frequency wireless power transfer should be stronger, such as much more energy should be delivered to these devices. For this, massive MIMO and the exploitation of high frequency uh, band seems unavoidable if we are going to target delivering high power levels. One needs to take advantage of the huge spatial gains that this technology can provide. In a very recent work, we studied the achievable performance of an indoor charging system. Basically, we have a room where the power beacons are equally placed in a radio stripe wrapped around a square perimeter of a room or office. In this figure to the right, we can observe how many power beacons can be equipped in the radio stripes as one increases the operation frequency. Of course, the greater the operation frequency, the greater the number of power beacons we can place because they can be closer to each other. And this number is for a certain distance separation between the power beacons and for a different number of antennas per power beacon. So we can equip a large number of antennas and power beacons in the radio stripes as we increase the frequency of operation. And we implemented the two-phase charging protocol where we have first sent uplink channel pilots for training, and in the downlink we implement wireless power transfer with the remaining symbols. In this case, the radio stripes are at the ceiling level where humans are unlikely to be, so we can operate relatively far, and therefore the MP is a more suitable metric. Also, we are operating at the high frequency, so in this case MP is also more suitable than the SIR. And we consider two types or two kinds of MP constraints. One related to limit the electromagnetic radiation in the proximity of the UV. So consider this is the UV, and we measure the electromagnetic radiation at the distance r in all the directions from the UV, and we constrain that power density at the distance rk, and we also constrain the MP seen at any point in the space. So this might represent a random human in the room. In this figure to the left, we illustrate the average radio frequency power density in the vicinity of the UV. So at the distance r from the UV, what is the power density when we implement, of course, the multi-antenna beamforming. And we establish this as the safety limit in our work, but the regulations are much more strict in reality. For instance, this is the ICNRP regulation, so it's very low. But we relax a bit this in order to facilitate the feasibility of the problem, because for satisfying these constraints, as we will see, we will need to operate at very high frequency levels. So let's say this is the constraint and this is the power density as a function of the distance. Of course, as we go far from the UV, the power density decreases, and we can only satisfy the constraints at the distance of 2 centimeters if we are operating at 28 gigahertz, and around more than 3 centimeters when we are operating with 4 gigahertz. And in the other figure, we display the cumulative distribution function of the RF power exposure in the room in any point. So we can observe that the chances of high radio frequency power exposure, like around 1 watt here, at a certain spatial point is very significant. It's very significantly small. So the main takeaways, and this is especially true when we go higher in the operation frequency. So the main two takeaways, or the main takeaway from this figure, is that the system becomes more electromagnetically friendly as the operation frequency increases, and this is because of the better spatial resolution, so the smaller wavelength. So we can point the energy towards a specific point more easily if we increase the frequency of operation. The main problem is that as the frequency increases, the frequency-dependent losses increase, and the required transmit power of the radio stripes increases as well, as it is shown in this figure. So here we are showing the average transmit power of the power beacon network as we increase the frequency of operation. As you can see, it is real that we can satisfy the electromagnetic radiation more easily, but we require much power at the transmitter side. Of course, we can improve or reduce that energy consumption by using more radio strips. For instance, this is if we implement 4-fold radio strips at the ceiling level, so we can reduce this power consumption here. This is the operation frequency of 4 GHz, which is the one that we adopted in the remaining figures in this paper. So we focus on the operation at 4 GHz, because when we go higher in frequency, it's very difficult to process the beamformings and to work with the proposed mechanism in this paper. So one of the main research directions that we propose here is in fact that how to implement our proposed mechanism at higher frequency of operation. We can see in this other figure here what happens if we increase the number of UEs, because the previous figures were if we have only one UE to be powered, to be charged. Basically, if we increase the number of UEs, of course, we require more power at the power beacon network. And the difference between implementing a different beamforming is not that significant, although of course it is preferred to implement the optimum, which is based on semi-definite programming. But we can still implement more like lower complex mechanisms like MRT or SCA based precoding, and still the performance will not be significantly degraded. But what would be the next steps for this kind of setup? Here we illustrate some interesting research directions to be pursued in the sequence. As we were discussing, or it was indirectly said, the efficiency of the considered system is considerably low, and it's usually in the range of 0.1 up to 1%. So to make the technology profitable and more sustainable, this energy waste must be reduced as much as possible. How do we do that? Well, by one alternative is increasing the number of transmit and receive antennas. So far, we only consider that there is only a single antenna at the receiver side. So in practice, these devices are multi-antenna devices. Let's say we have a 4 cm by 4 cm space to place the antennas at the receiver side. If we operate at 4 GHz, we can deploy 4 antennas in that form factor. If we operate at 28 GHz, we can deploy up to 71 antennas. If we go to 100 GHz, we can deploy this amount of antennas. It's enormous. Of course, the energy consumption of such system increases as well. So it is important to see, to take into account all these factors and see what are the performance gains, what is the attainable system efficiency in a system like that. Also, as we see, there is increased energy waste when serving multiple users simultaneously. So we need intelligent schedule mechanism such that we can schedule less devices simultaneously. Of course, it is also more difficult to control the electromagnetic radiation if you have to power many devices simultaneously. So that's another reason to investigate more intelligent schedule mechanism. Also, each power beacon needs to inform the estimated CSI to the central processing unit over limited capacity from whole connections. We assume so far that these links are ideal, so we have infinite capacity and instantaneous transmissions here. So we need to investigate what happens if we don't have such idealized system conditions. So what happens if we take into account also the quantized channel state information and the energy beamformers can degrade accordingly. Those are very interesting directions to continue researching in the sequence. So regarding the question whether 6G will provide radio frequency wireless wire transfer services or not, we can say that we envision that these networks will have the capability to do so. Will they do it or not? That's more difficult to answer, but they will have the capability to do it, is our belief. And why is that? Well, basically, the 6G research is developing in 5 fronts mainly. In the exploitation of new spectrum and the extreme massive MIMO. So we are moving to very high frequency operation, but also to mid frequency and also to low frequency operation, like a spectrum above 92 gigahertz, in between 7 and 20 gigahertz, and in very low frequency bands as well, for different kinds of networks and use cases. As we were saying, the exploitation of very high frequency is very beneficial, and also the exploitation of very massive number of antennas as well. So this is a point in favor of supporting radio frequency wireless power transfer. Also, there is the potential also to support joint communication and sensing. So future networks are expected to sense the environment more natively, and this sensing is fundamental to promote, in the case of radio frequency transfer, to detect the humans in the loop and prevent exposure, electromagnetic field exposure above the limits available. Also, of course, there is a fight of security, trust, and privacy, with having the data or the energy profile of the devices is a sensitive data that must be taken care of. Also, there is a notion of in-exum networks. Basically, we have like a very short-range networks which can operate offline, I mean without the main connectivity to the cellular network, but when they are connected to the main network, they can operate better. So this is a nice notion that is incorporated in the 6G research. And also we have the native AI interface, so AI to enhance the physical communication. So in the context of 6G, we can say that radio frequency wireless power transfer can be considered to enable in-X charging subnetworks. For instance, we can have a charging network in a home to power our appliances and other wearables. And also we are going to exploit high frequency bandwidth operation and the network sensing for detecting the human in the loop, using AI with all the data generated by these charging networks. And of course, we need security and trust in as well. Coming to the conclusions, we can say that sustainable systems must be green, profitable, and fair. And the traditional charging technologies which relies on wires or batteries are in fact not sustainable, not applicable always and everywhere, and in many cases not appealing as well. And these issues can scale quickly with the number of devices. So the technology of radio frequency wireless power transfer is promising to address the above issues, but a set of challenges must be efficiently addressed, and those are related to the low power transfer efficiency, especially end-to-end, the fear of wireless, and the lack of standardization. And during these slides, we also discuss many potential enabler solutions and some specific examples and research directions were also analyzed and identified. At the end, a holistic system optimization is needed, and much more effort is needed in that front as well. To conclude, I would like to thank you for the invitation and for listening to my talk. And I would like to conclude that if you have any questions, doubts, feel free to let me know. And also you can contact me via email and also consult my personal webpage as well. There is a book that was recently published by Wiley where many of the content discussed in this talk is there. And we also have like a special issue on MDPI sensors, which is open until February 2023. The idea is that we receive submissions and we publish as long as they are accepted. I mean, you don't need, if you are interested, you don't need to wait until February 2023. You can submit earlier and it will be processed accordingly. So you are welcome to submit. Also, if you are interested in joining the CC flagship, we have currently a recruiting campaign and you can drop your application to me directly by email or directly in this website. So thank you very much for listening. See you next time.